Good morning, gentlemen. Today we're going to talk about discriminating scanners. We're going to look at some typical applications, and we're going to talk about Fireye's range of scanners to kind of give you an overview of what's available and how the technologies relate to the basic principles. Typical applications would include utility power generation, where we normally would see pulverized coal with either gas or oil igniters, pulp and paper applications, petrochemical refinery type applications, incineration, biofuels and waste treatment, as well as duct burners, kilns, and industrial ovens. Beginning, typically early scanners would have an amplifier and a scanner. Those scanners in the Fireye variety were the 45 UV5, which used an ultraviolet tube, and the 45 RM4, which used a infrared sensing tube. These again went to the amplifier. They relied basically on sighting, orifices, and manual adjustments of bandpass filters to provide discrimination between the target plane and background planes. The Fireye signature scanner provided a breakthrough in that it learned the signature of the target plane based on flicker frequency, amplitude, and the regression slope, and then it compared those factors to the background planes. Current scanners are integrated. They don't use a separate amplifier. It's all built into the scanner. This saves wiring cost and troubleshooting time. They're all microprocessor based, and all but the most basic applications will use solid-state sensors as well as electronic self-checking circuits. They can either be single ultraviolet or infrared type sensors, or they can be dual sensor scanners that have both the UV and IR sensors in one scanner. If required, they can utilize fiber optic bundles to optimize sighting in the target plane, and most modern day scanners have communications built in, so you can bring back the entire appliance and multiple scanners to a single point, view it on your computer. And they also have multiple file selection for different combustion conditions. The first scanner in Fireye's current generation is the Simplicity. That is a tube type still with a photo-optic shutter. It doesn't require any programming. It's been around for a long time, and there's lots of them out there. Gives you a 4 to 20 output, as well as the contact closures. Increasing in complexity, we move up to the Scenic scanner, which has a solid-state sensor, either UV or IR. Also has a solid-state self-check network, powered by 24 volts DC. Provides a contact closure back for flame relay, a false contact back if there's an internal fault in the scanner, and a 4 to 20 output supply. To name a 4X, Class 1, Div 2, A, B, C, and D. The scanner actually learns the flame automatically through an auto-tune process. And you also learn the flame off condition, and it compares the two. Then we move up to the InSight and InSight 2 scanners. These also are solid-state sensors, either UV, IR, or both sensors located in one scanner. They have a solid-state self-checking network as well. Again, there's an auto-tune process where we can learn the target flame on, and we can learn the background flames as our off condition. We select from 21 different flicker frequencies, provide a 4 to 20 milliamp output for flame strength. There are multiple files to choose from. In addition, all the parameters are editable by the operator. Finally, we offer the Paragon scanner, which does not only flame supervision, but temperature measurement. It provides dual 4 to 20 outputs, one for flame strength and one for temperature. It's password protected. It does the auto-tune, learning the flame on and flame off. This is a good application for power generation. If you've got a utility boiler that may have 24, 48 burners in it, pulverized coal, there's no way you can use oxygen to know which burner is going out of ratio. So when the burner is initially set up, we find the flame temperature. If that burner starts to drift, we're able to make corrective action and pinpoint which burner is drifting. Applications for this might be a power generation plant where maybe you've got 3 decks, 24 burners, coal-fired. You can't really use oxygen to know which burner is going out of ratio, but if you sight it for temperature at optimum ratio, then you get an indication. We go back to the 101 course. We remember that infrared is 90% of the flame, most strongly at the outside edges of the flame, visible about 10%, and UV is about 1%. The strongest UV signal is found in the primary combustion zone, and it's nearest the burner head. If we look at typical detector sighting, we want to get through that primary combustion zone. This is where you're going to have the highest frequencies. Remember that a flame is a series of small explosions because of the mixing and turbulence and the propagation rates. The most explosions are going to occur in that primary combustion zone most rapidly, and that's going to produce the highest flicker frequencies. It's also going to have the lowest amplitude or brightness. So the brightness is going to be greater near the edge in the flame envelope instead of the primary combustion zone. If we're able to sight through the primary combustion zone, we can then tune for those higher frequencies and tune out the lower frequencies. We also have to take into account the swirl. Here you can see it's a counterclockwise swirl. That's the actual igniter there, and the sighting port for the scanner is down here. Because we're looking at the air sweeping around and sweeping that combustion zone down. If we remember that we're going from highest to lowest flicker frequency, but lowest to highest amplitude, and we get a graph that looks something like this. Here's our background flame, which is going to have high amplitude at lower frequencies, and then lower amplitude at higher frequencies. A flame-on condition will give us a slope that looks something like this, a fast Fourier transitional slope or transformation slope. So if we want to tune between flame on and flame off, we're going to try and pick a frequency that's going to have a good distance between it. So in this example, we can see that around 75 hertz, we're going to be able to distinguish between a flame-on condition and a flame-off condition. And that's one of the tests that a discriminating scanner is going to use. Again, the flame flicker, say that 100 times. Flame flicker is greatest near the primary combustion zone and lowest during by the flame envelope. When we try to line up the scanners, what we want to do, of course, is, in this example, would show an opposed fired furnace with burners on opposite walls. We're trying to get to that primary combustion zone. If possible, avoid seeing the flame that is on the opposite wall. Sometimes we're not able to do that. In that case, you still want to come through the primary combustion zone on our target flame, and if we have to look at the opposing flame, we want to try and catch the edges where we're going to have the lower frequencies. So in a flame off condition, if we tune for the higher frequencies, even though we're going to see the lower frequencies here, the scanner is not going to pull in. Typically, the more you sight out of the primary combustion zone, the less likely you're going to be able to discriminate between flames. We look at the black line here, we can see that we're catching the flame envelope. We know that there's going to be lower frequencies and higher amplitude there, and that's going to be very similar. If we go back up, that's going to be very similar to what the scanner would see on a flame off condition. So again, we want to try and get through the primary combustion zone where we can discriminate between areas of flame and the different flames themselves. Here's scanner aiming. If this was an opposed fired furnace, again, 6-burner type application, we could see that we got a not very good situation here because we're going to be at high fire. There's just going to be a ball of fire in there. We're catching some of the primary combustion zone on this one, not very well there. So good scanner aiming in a multi-burner application would be typically mounting the scanners on the inside facing the outside walls of the outside burners. And then on the central burner, we would want to avoid, if possible, the red line, because again, that's going to go into the heart of the opposite flame, where this one will try to catch the edge of it but not hit the other flame. Sometimes that's impossible, and that's when we have to go to exotic type solutions such as fiber optic, where we would run either a quartz bundle for ultraviolet or a glass bundle for infrared. We'd actually bring that into the throat of the burner, tilt it around so we would be looking at an angle such as this. We also provide skewed lenses so that if you can't run the bundle at an angle, you could run it straight, but the skewed lens is going to look into the flame and not see the others. So the typical tests that we use are flicker frequency, amplitude, and the slope to get a picture of the target flame. We then compare that picture to the other variables when the flame is off. Here's a typical InSight scanner and the mounting. We're going to use a swivel that'll allow us to sight for optimum sighting of the target flame and try to avoid sighting the other flames in the combustion chamber. In this particular example, there's a Y for cooling air. There's a sealing union with a lens in there for a high pressure application. And we make a fiber nipple, which helps with heat. And then our mounting flange and scanner. If we had a low pressure application, we wouldn't need the sealing union or the Y. We could come with this nipple straight into our swivel, and we have a 3/8" port that's built into the flange to provide cooling air. A typical InSight scanner is going to have 3 layers of menus. The outer layer of menu will give us flame quality. Flame quality is a number that Fireye uses to indicate the overall status. It's capped 100. So flame quality can run from 0 to 100%, even though our pulse counts for infrared and UV could be greater. So if we had a pulse count of 80 for infrared and a pulse count of 80 for ultraviolet, the total count that the scanner sees would be 160, but we would cap that at 100 for our flame quality number. This allows operators kind of across the globe will to use a standard scale on a quick walk by. They can look at it and say, yep, I got a 90% flame quality, I'm good, instead of trying to correlate counts versus what the maximum count was and what is a good count at that moment. The next item in that menu, outer layer menu, is whether your flame relay is on or off. Some people will leave it there so they know if it's seen the flame or not. Temperature is available in Fahrenheit or centigrade, and then there's 4 files to select from. And that will tell you which file you've selected. You also are able to see that pulse count that I referred to earlier in the flame quality, and that is the raw count of flicker that it is seeing. Communication address, again, we use Modbus, so the address is there, the date, the maximum temperature that the scanner has seen, and then there's an entry for password, which would take you into the other 2 menu loops. One is the edit, the other is the auto-tune loop. If we went into the auto-tune loop, we would do something that is called AIM scanner. That slide is actually a mistake there. It's going to give you a number for Fireye of 0 to 60, and we say that 10 to 26 is a good range. It's an arbitrary range that our engineers made up. If you are above if you're above 26, you're getting saturation, and you typically need to re-aim the scanner. So what it's trying to do is to guide you to sight the scanner into that primary combustion zone. Once you do that, the swivel would be tightened down, and we would do what's called a learn-on procedure. In a learn-on, we have our target flame running at low fire, and we have the adjacent flames turned off. 128 seconds later, after we push the magic program button, it has learned the characteristics of that flame, again, based pretty much on the slope, the amplitude, and the flicker frequencies. At that point, we turn the target flame off. We turn all the adjacent flames on to high fire, so we've got as much background in the combustion chamber as possible. And then again, we hit the program button, and at that point, the scanner is going to learn the flicker frequencies, the amplitudes, and the slopes of the flames that's seeing there. If the scanner has been sighted properly and there's enough difference between the flames, we're done. It's learned to discriminate between the two. If not, gives you that warning message that says poor discrimination, re-aim the scanner. So that's the auto-tune function. On an InSight type scanner, you also can go into the edit mode and go through all these selections manually. So if we start down here at the bottom, file select, again, you have 4 files to choose from for different combustion conditions. An example, a couple of years ago, at a refinery up in Lima, Ohio, and what was happening is they were losing on some outdoor equipment. They were losing their flame signal in the fall and the spring, and it turns out on studying that, what happened was when they had high humidity and low temperatures, they were generating steam with their combustion air inside, and the steam moisture was absorbing the UV signal. So what we had to do was learn the steam type condition for combustion at normal, and so they would just switch it by remote communications during those times, and everything worked out well. We also have the communication address. the temperature scale select, how we want to select our remote files, either by keypad, communications, or digital input. We also have the ability to copy one file to another, a language selection. We can manually adjust on the dual scanners whether we're going to use the UV sensor, the IR sensor, or both. An example where you might want to turn off one of the sensors would be at a black liquor boiler in a paper processing plant. The black liquor, generally, they can't turn that off when you're setting up scanners, and it's hugely infrared, lots of orange flames, that stuff dripping everywhere. But it's sustained by gas burners. Gas burners are rich in UV, and so you would go to straight UV, set for the higher frequencies, and you're actually able to tune in and see the gas burner against the background of all the black liquor burning. Next, we would select the IR band. Again, there's 21 different flicker frequencies. Here you can see in the example they set it at 23. And that would pretty much cite everything. And then if we were actually looking at a flame, we'd have a pulse count there. We're able to manually select the gain. Gain goes from 1 to 31 on a Fireye scanner. For each number you increase the gain, you're going to increase the pulse count by about 50%. So if that IR band of 23 was getting a count of 60, by increasing the gain from a 1 to a 2, you would add 30 to that, and that count would go up to about 90. So gain is kind of like chief. Infrared range, either high or low range. If you're getting too much saturation, you can switch to a low range, which has a lower overall gain setting, or front-end gain, FEG, as we call it. Then we would swing around, and we can manually adjust the UV side, band, gain, range. And then for pulling in the flame relay, we set an on threshold and an off threshold. Standard Fireye defaults are 40 and 20. Those are based on flame quality. So no matter what type of pulse count you're getting, if your flame quality is better than 40, the scanner's going to pull in. If it drops below 20, it will drop out. Then we do the flame failure response time. For safety reasons, it comes default at 1 second from Fireye. Generally, that's not a good setting because your relays chatter on and off anytime you get any movement in that flame. So normally 4 is a very good setting for that. And then finally, on-time delay, which is the amount of delay before the flame relay actually pulls in. And again, to avoid chattering, I generally set that for 2 seconds. Okay, so that was kind of a walkthrough of how one of our scanners would be set up without going heavy into the theory. Typically, we're going to base it on flame flicker, amplitude, and the slope. Any general questions?
I don't have any questions popping up at this point, Dave.
Okay. Sounds like it's a wrap. Thanks, guys. I don't know, Mike, if you had a chance to look at. We do have a manual that's available. It's called WV96. You can send an email to Mike if you want that. It goes into a lot more detail on the general principles of multi-burner scanners. It's about 30 to 35 pages long, and it's free. So if you have an interest, in email
I'll go
to
ahead.
Mike.
Yeah, I'll go ahead and send it out to all the attendees so that they can get a copy of it.
Great. Thanks for your time, everybody.
Yeah, Dave, thank you very much for your presentation. If anybody does have any specific application questions, please feel free to call me directly. Our phone number is 800-9-LESMAN or 800-953-7626. And again, feel free to ask for me, Mike DeLaCluse. Dave, thank you very much. And with that, we will conclude the presentation.
Thanks, everybody. Bye.